Good day. Today we will tell about the methods for determining the concentration of point defects. You can see the plan. All methods are derived to groups. The first group, the measurement of the physical properties of crystals, and the second group, the experiments using the quenching. The first group includes methods that use the measurement of physical properties at different temperatures. In another group of methods, experiments using quenching are used. Excess concentrations of vacancies obtained during quenching from high temperatures gives an increase in the specific electrical resistance. The and state of point defects are determined by measuring the crystal densities, lattice parameters, ion conductivity, or electrical resistance. The specific volume and correspondingly the length of a sample of a metal or alloy increase in proportion to the concentration of vacancies. Since vacancies scatter conduction electrons, electrical resistance also increases in proportion to the concentration of vacancies. The measurement of physical and electrical properties is most often used to determine the concentration of vacancies. Methods for determining these properties can be divided into groups. The first group, I repeat, includes methods that use the measurement of physical properties at different temperatures. Data on the concentration of vacancies can be obtained by comparing the change in the length of sample with change in the lattice spacing upon heating. The discrepancy between the increase in length and the increase in the lattice spacing gives information on the equilibrium concentrations of vacancies. Here you can see some formulas for determining the concentration of point defects. In details, we will discuss the protocol of calculation of these concentrations of vacancies further in the next lecture. Having determined the temperature dependence of the concentration of vacancies and using the quotient of equilibrium concentration vacancies, we can calculate the energy of their formation. We can also apply another indirect method of determining the concentration of vacancies. At low temperatures, the electrical resistance increases linearly with temperature. At high temperatures, the experimental points don't fall on a straight line, giving positive deviation. If we assume that additional electric resistivity arises from an increase in the concentration of vacancies and is proportional to this concentration, then we have the special quotient. Having plot the graph, this quotient in the coordinate electricity resistance and the temperature, we obtain a straight line whose tangent of slope is equal to the energy of formation of vacancy E. Then it is easy to calculate the equilibrium concentration and derive it big N. In another group of methods, experiments using quenching are used. Excess concentration of vacancies obtained during quenching from high temperatures gives an increase in the specific electrical resistance ρ. Assuming that as a result of quenching from the temperature, the increase in the electrical resistivity. And then we get this equation. Having built the graph in coordinate ρ and temperature of quenching, by slope we determine value E, and by its value we calculate values n derived big N at different temperatures. Below you can see the result of determining n deriving big N by varying the length for some metals near the melting point. You can see gold, silver, copper, aluminum and lead. It means that this digital means that so this quantity of vacancies accords to 10,000 of particles. It is a good concentration. This alloy or metals is a stable condition. Thank you.